So we've introduced work, and work is a way to transfer energy from one place to another. But we wish to look at a total energy approach to mechanics problems. So we need to introduce some other energy terms. For instance, kinetic energy. Work can cause a change in energy of a system. For example, consider a constant net force on a particle for a distance x. What we're going to say is that the force that you are exerting on this block is the net force. So we're going to say there's no friction, no other forces. This is your net force, and we're going to exert this force for some distance x. So the work done would be equal to that force times that displacement, that distance x in this case. It's your net force. It's the only force. So according to Newton's second law, that's equal to ma. So you have the work is equal to mass times acceleration times x, which we could write as mass times acceleration times x. Since it's a constant force, we have constant acceleration, and we can pull from kinematics that the final velocity squared will equal the initial velocity squared plus 2 times acceleration x in this case. We could use delta x, but our initial position is 0. So ax is equal to final velocity squared minus initial velocity squared divided by 2. Plug this into the previous formula, and we have work is equal to mass times final velocity squared minus initial velocity squared divided by 2, which we could write as 1/2 mass final velocity squared minus 1/2 mass initial velocity squared, which I'm going to say is the change in kinetic energy if we define kinetic energy as 1/2 the mass times the velocity squared. So this is our final kinetic energy minus our initial kinetic energy. So we have defined the energy of motion, kinetic energy, as 1/2 the mass times the velocity squared. So any mass with some velocity will have a certain amount of kinetic energy. And we can see that this kinetic energy is proportional to the mass and proportional to the velocity squared. So the larger the object is, the more kinetic energy it's going to have. But the faster an object's moving, it's going to have a lot more kinetic energy. For example, when a car doubles its speed, its kinetic energy will increase by 4 times. If you have a speed bump and you're wondering whether you should go over that speed bump at 5 miles per hour or 10 miles per hour, well, at 5 miles per hour there'll be a certain amount of kinetic energy associated with that contact, and if you stop, then that kinetic energy might go into damaging your car. Whereas if you go at 10 miles per hour, you're going at twice the speed, 4 times the kinetic energy. So if you stop then or crash then due to the speed bump, you'll have 4 times as much damage to your car. So you want to honor the speed bump. And another example, recently we had a asteroid come pretty close to the Earth, and you always wonder, well, these asteroids some of them are only, a couple of 100 meters in diameter. They're relatively small rocks compared to the Earth itself. How can they have that much energy? And the reason is not so much to their mass, but the fact that they're moving so fast. They might be moving 30,000 meters per second, 30 kilometers per second, and when you square that kind of velocity, you're going to end up with megatons of TNT of energy, multiple values of equivalencies to the atomic bombs, all associated with one rock moving really fast. So there can be a lot of kinetic energy. It goes with the velocity squared. For completeness, note that this last result can be derived using calculus. If I say my net work is equal to the integration from initial to final position of my net force dx, and that's equal to ma dx, but then we're going to use a little bit of mathematical wizardry here. We're going to say that the acceleration is dv dt, and I'm going to say dv dt is the infinitesimal change in velocity per dx times dx dt, which I can write as dv dx times the velocity dx dt. I'm going to substitute that in for acceleration. The dx's cancel out, and I'm going to have integration of mass velocity dv. Mass is a constant. I can take that out of the integral, and then I can integrate v dv, which is a simple integral. It's just 1/2 v squared. Evaluate it from initial to final velocity. So this is 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. My final kinetic energy minus my initial kinetic energy, my change in kinetic energy. So that's a different way of coming up with the same result using calculus. All right, so work can cause a change in kinetic energy, a change in the energy of motion. It could also change your potential energy, your potential to do work in the future. Here's how it might work. Let's say you had a mass at some particular height, and you apply a force on this mass equal to its weight, actually, so that you're lifting it up against gravity. And you lift it up for some distance d. So you actually do work on it. You apply a force equal to gravity, mg, and then you apply it for some distance d, so you do positive work on this mass as you lift it up. So the work would be equal to your force times the distance d, mg times d. But we could define d in terms of your height. We can say your original height of h1, and you go to a final height of h2, so the distance d is equal to h2 minus h1. So the work is mg h2 minus h1, which we could write as mg height 2 minus mg height 1. I'm going to define mg times your height as your gravitational potential energy. So this is your final potential energy, U2, which we're designating potential energy as U, minus your initial potential energy, U1, or your change in gravitational potential energy. So the work is going to cause a change in gravitational potential energy, giving you more potential energy than you had, so now you have the potential to do that work back. So we've defined U as potential energy, in this case gravitational potential energy, mgh. It really depends on where you define your h from as to how much this potential energy is going to be, and you have your own prerogative as to where you want to define your 0 point for your ground level or for your h. You can define it strictly from ground, or any other height. You can define your mgh from any other height, and you'd be fine as long as you stick to your guns. Whatever problem you're working on, if you define a particular height as being your 0 height, then you have to make all your definitions from that height. But if you do it that way, then you'll be fine. So you can define any height as your 0 point as long as you stick to it throughout the problem. This gravitational potential energy only depends on your vertical height against gravity. It doesn't depend on your horizontal extent through the problem, because there's no force in that direction. So you only have to worry about your vertical height between 2 points. If you're on this roller coaster, we'd only be comparing our gravitational potential energy between height h1 and height h2. That's all that matters. For example, if we look at this incline, we have a mass on this incline. Let's say it's going to slide down this incline some distance d, and the angle of the incline is theta. What we're interested in is what is its change in height. So what we can do is define our final position as our zero height. We always want to possibly look at the lowest position within the problem as being our zero position. Then everything else is defined above that. So that would be a good way to choose where your zero height is. Just look at the problem, read the problem, find out where your lowest position is going to be, set your zero at that point. So in this case, we're sliding down to this point. We set our 0 point there, but we're interested in h, which is really the height above that 0 point. If I look at this right triangle here, d being the hypotenuse of that right triangle, h is equal to d times the sine of theta. So I can deal with the potential energy mgh, where I define h, in this case, as d sine theta. All right, so we've introduced kinetic energy, we've introduced gravitational potential energy. It turns out gravity is what we call a conservative force. By conservative, we mean the work done by gravity is independent of the path. You can go up, you can go down, up, down, and wherever position you are, the gravity, the work done to that position will be the same. So there's no dissipation along the way. So the work done by gravity is zero for a cyclic path. For a conservative force, you can go there and back again, and there's no total work done if you go a cyclic path back to where you started. So if we have a conservative force, we can use this concept of potential energy. We can say that wherever we do go, we're storing energy so that we can have it back again if we come back. So instead of dealing with gravity as an external force doing work in our problems, we're going to use conservative forces as being responsible for potential energy. And so we're going to deal with gravity strictly with potential energy, mgh, and that sort of thing. On the other hand, friction is a non-conservative force. That means it leads to a loss of mechanical energy if you go from point A to point B, and hence the work done will dissipate energy from your system, and it's not cyclic. So it depends on the path you take. So we're going to deal with friction as an external force doing work on our system. If we have only conservative forces, then energy will be conserved all the way through whatever path we take. And we'll have conservation of mechanical energy. Our total energy will be equal to our kinetic energy plus our potential energy, and that will be a constant. Hence, if we choose an initial point at an arbitrary point A and our final point as an arbitrary point B, the initial energy at A should equal the final energy at B, which we could write as the kinetic energy at A plus potential energy at A. The total energy at A should equal the kinetic energy plus potential energy at B, the total energy at B. How we got there doesn't matter. And so this is rather independent of time. We can just look at the point A, feel the energy there, look at point B, feel the energy there, compare the two, and solve for our unknown. Not worrying about how it got there, the path, or what time these points occurred. That is the beauty of the energy approach. In the case of mechanical energy for a freely falling body, we write these terms out. So we have kinetic energy at A, 1/2 mass times the velocity at A squared, plus the potential energy at A, mg, height at A, is equal to the total energy at B, which is kinetic energy, 1/2 mass velocity at B squared, plus the potential energy at B, mg, height at B. Let's try this out in a problem. Here's a problem. Dave Johnson, the bronze medalist at the 1992 Olympic decathlon in Barcelona, leaves the ground in the high jump with a vertical velocity component of 6 meters per second. How far does his center of mass move up as he makes this jump? Here's an actual picture of Dave Johnson, bronze medalist at the 1992 Olympic decathlon. He probably was not satisfied with the bronze medal, but that's what he got. The reason he might not be satisfied is because going into the Olympics, he was one of the top 2 decathletes in the world, and both of them were Americans. There was Dave Johnson and Dan O'Brien. They were the top 2 decathletes in the world, rated 1 and 2. And so Nike employed them both in a very expensive advertising campaign. And the question was this competition between the 2 of them at the Olympics. Who was going to win? Was it going to be Dan or was it going to be Dave? Was it going to be Dave or Dan? And it showed them competing against each other as Dan or Dave, Dave or Dan, Dan or Dave. And they had millions of dollars in this advertising campaign, but they didn't count on the fact that the Olympic trials, the United States Olympic trials, were 1 month before the Olympics. And at the Olympic trials, Dan O'Brien, who had never missed at the starting height of the pole vault, which was about 14.5 feet, scratched on his first attempt, scratched on his second attempt, and hit the bar down on his third attempt. So he totally scratched out of the pole vault, got 0 points for the pole vault, and finished 4th at the United States Olympic trials and didn't make the Olympic team. So only Dave made it to the Olympics. The Nike campaign was a total disaster, except for now I'm still talking about now, so they probably got a lot of advertising out of it. And Dave Johnson should have been the favorite at the Olympics, but ended up with a bronze medal. Okay, back to the problem. He's taking off from the ground with a velocity component of 6 meters per second. We want to see how high his center of mass goes. So we're going to select our lowest point as where his center of mass starts at when he's on the ground. And that's going to be our point A. And then his highest point is going to be point B. He's going to go as high as he can go, and then he's going to go no further. So we're going to compare these 2 points and feel the energy at A and feel the energy at B. Well, the energy at A is 1/2 mass times velocity at A squared plus mgh, height at A. That's his total energy at A, kinetic plus potential. And at B, we have kinetic plus potential as well. So we set up our equation. These energies should be constant. There's no dissipated forces along the way. Before we go any further, though, one or more of these terms might actually be 0. Which terms are actually 0? Well, we can choose point A as being our 0 height. It's the lowest height in the problem, and hence height at A would be 0. Height at B would simply be the height above that point. So we can select the height at A to be 0, and then that term is gone. Sounds good. Are any of these other terms 0? Well, he's going to jump off the ground with some velocity. He's going to go as high as he can go and go no further. So he's going to momentarily stop at point B. So his velocity at B will be 0, and hence his kinetic energy at B will be 0. So the velocity at B will be 0, the kinetic energy at B will be 0, that term's gone, and all of a sudden our equation's gotten easier. We're left with 1/2 mass velocity at A squared equals mg height at B. Sounds good. Let's solve this. Well, his mass is still the same, so we can cancel that out on both sides and solve this for his height at B. We're going to divide both sides by g, and then we have it. So his height at B is 1/2 his velocity at A squared divided by g. That's 1/2 times 6 meters per second squared divided by 9.8. His center of mass is going to go up 1.84 meters before to his maximum height. How about that? See how nice this is? How nice this energy approach can be? Incidentally, if he were a high jumper, he could probably go even higher above the bar by bending his body over the bar, maybe with a Fosbury flop. Put your head over first before you kick your legs over, and you can maintain your center of mass below the level of the bar, and that way you can actually achieve a higher height than where your center of mass actually goes. Just a word of advice. Here's a special case. If we were to drop a mass starting from rest to a lower height with no dissipative effects along the way, what would happen? Well, let's set our lower height as being our zero height and set up our mechanical equation, point A being the first height, point B being the second point. We have our conservation of energy, kinetic energy at A plus potential energy at A equals kinetic energy at B plus potential energy at B. In this case, we're going to start from rest at A, and so our velocity at A will be 0, that term will be 0, and we're going to set our height at B as being 0 because that's our lower height. So we're going to set the height at B to be 0. Now our equation looks like this, mgh equals 1/2 mass times velocity of B squared. So if we set our height at A to be h, and our velocity of B to be our final velocity v, cancel out a mass on both sides of this, solve this for our final velocity, multiply both sides by 2, and take the square root. Our final velocity will be the square root of 2gh. This is a special case of conservation of energy, but it comes up quite a lot. So it's kind of a nice little formula to have handy, where you start from rest, you go to a lower height, and your velocity at that lower height is the square root of 2gh, independent of your mass, and it only depends really upon your value of your height. So very useful formula to have in your back pocket when dealing with conservation of energy. Velocity is the square root of 2gh. Let's actually try it out on a pendulum. A simple pendulum consists of an object suspended by a string. If the string is 2 meters long and makes an initial angle 30 degrees with the vertical, calculate the speed of the particle at the lowest point. Take a look at a pendulum. And we want to find the speed of this pendulum as it comes down like this. Well, we need to find its height, and then its speed at the bottom should be equal to the square root of 2gh. Finding the height is going to be the hard part. Maybe not too hard. If I can say that my total length is L down to the bottom, then my length from the pivot point up here is equal to L cosine theta in this case, theta being 30 degrees from the vertical. So the difference between those two distances, L cosine theta and L, total L, will be my height. Cool. So height will be equal to L minus L cosine theta, in this case 2 meters minus 2 meters times cosine 30, or 0.268 meters. That means my velocity at the lowest point will be the square root of 2gh, because we started from rest and went down to a lower height. 2 times 9.8 times 0.268 square root, 2.29 meters per second. All right, so we've introduced potential energy, but there's another potential energy other than gravity potential energy that we wish to consider. It's also associated with a conservative force, the spring force. We saw in Chapter 7 that we can do work on a spring by either compressing it or extending it a distance x, and the work we do was equal to 1/2 kx squared. So if we did compress it, now the spring has that energy stored in it and it has the potential to do work back equal to the work that we did, 1/2 kx squared. Or if we extend it, the same thing. It has the potential to pull it back and do work equal to the work that we did to extend it, and that is 1/2 kx squared. So a spring, either compressed or extended from its initial equilibrium value, will have stored energy equal to 1/2 kx squared. So we have two forms of potential energy: gravitational potential energy, mgh, spring potential energy, 1/2 kx squared. And we'll be using either one of these or both or none of these depending on the problem. If the problem has a spring in it, then we have to worry about 1/2 kx squared. If it changes height, we have to worry about mgh. Let's try another problem. A block of mass 0.25 kilograms is placed on top of a light vertical spring of constant K equal to 5,000 newtons per meter. It's pushed downward so the spring is compressed 0.1 meters. After the block is released, it travels upward and then leaves the spring. To what maximum height above the point of release does it rise? So here's a spring. We put a mass on it. We push the mass down. We let go. At that point, it starts to move, and it will leave the spring and go flying in the air, and at some point reach some maximum height, and that's what we want to find. But we're going to use conservation of energy to do this. We'll look at point A and point B. We'll select the height at point A to be our zero height, and then B will just be our height above that point. The energy at A should equal the energy at B, or strictly speaking, the kinetic energy at A plus potential energy at A should equal the kinetic energy at B plus the potential energy at B. The kinetic energy at A, 1/2 mass times velocity squared. Potential energy at A, 1/2 kx squared plus mgh, two potential energies to consider here. Same kind of form for point B. So here's my equation. My next question is, which, if any, of these terms might actually be zero? Well, when we first take our hand off to let the spring decompress, we still haven't started to move yet. So our velocity at point A is going to be zero, and we have no kinetic energy at point A. Very nice. Also, we'll realize that when it finally gets to point B, we're going to momentarily stop at that point, because we're as high as we can go and go no further. It's going to momentarily stop at the greatest height, and hence our velocity at B is going to be zero as well. So we have no kinetic energy at point B. Two terms gone already. So even though there was kinetic energy along the way, because we're using this energy approach, we're only interested in 2 points, A and B. And if we select those points correctly, or best, then we can simplify the problem. And in this case, we don't have to worry about kinetic energy because we chose the right 2 points. What else might be zero? Well, we're going to define our lower height as being our zero height, so the height at point A will be zero. Hence, mg height at A will be zero. So that's zero. Things are getting easier. And we know that at point B, the spring is already sprung and will spring no more. So there's no more potential energy in the spring when the block gets to point B. So the x is equal to zero because the spring is sprung. It's right at equilibrium now. And so at point B, our x is zero. Now this equation is a whole lot easier. 4 of the terms are gone. And we have that the potential energy in the spring at point A is equal to the potential energy in height at point B. We want to solve this for the height at point B. Divide both sides by mg, and we get that the height is 1/2 kx squared over mg. 1/2 times our K constant, 5,000 newtons per meter. We compress the spring at distance x equal to 0.1 meters. Square that. The mass was given as 0.25 kilograms. G is 9.8. This thing will go up to a height of 10.2 meters. How about that? This is a more complicated problem than anything we dealt with dynamics. We got a spring involved. We got gravity involved. We're moving, and yet it's a relatively easy problem to solve using energy considerations. Well, we're dealing with situations where we have conservative forces and energy is conserved from point A to point B. What would happen, though, if we introduce a non-conservative force like friction and energy is not conserved as you go from A to B? What do you do then? Well, we have a little bit of an addition to our treatment so far that will account for this. We can adjust for this by saying that whatever energy we start with, our initial energy, plus whatever happens along the way due to work, either positive or negative, should equal our final energy. So what we start with plus whatever we add or subtract along the way due to work will equal our final energy. Pretty straightforward. Makes sense. So the energy at A plus whatever work done on the system, positive or negative, will equal the energy at B. Or we write it like this. The kinetic energy at A plus potential energy at A plus any work done on the system along the way will equal the kinetic energy at B plus the potential energy at B. This is your one equation to rule them all. For all of our energy problems, we can start with this equation and we got it. So this is an awesome equation. This is the one equation to rule them all. If you're doing a test on this subject matter and you simply wrote this equation down on an energy problem, you'd be sure to get at least a little partial credit, because this is the way to start all of our energy problems. Any work on the system changes the total energy of the system, positive or negative. We could say the work on the system is our final energy minus our initial energy, or a change in energy. Or we could write this as the work on the system is equal to our change in kinetic energy plus our change in potential energy. This is a different form of that one equation to rule them all. Sometimes useful, just a more obscure form, kind of nice to have. But in general, the one equation to rule them all is something you can start with all the time. So here's our problem-solving strategy. Start with kinetic energy at point A and B, define it, and potential energy at point A and B. Define all your energy sources at A and B. Feel the energy at A, feel the energy at B. Kinetic energy is always 1/2 mass times velocity squared. So you have things moving at A, then you have to assign kinetic energy to them. If you have things moving at B, assign kinetic energy to those. Potential energy, there's two of them. MGH, so if you have a height at A or B, you assign an MGH to them. Or a spring, if you have a compressed spring or extended spring at A or B, you have to assign energy to it equal to 1/2 kx squared. So these are your initial energies at A and B. For the height, you want to select a reference for your zero height in the problem. Usually select, if you read the problem, select your lowest height within the problem as being your zero height, and everything above that will be positive. If you made a mistake and you select some other arbitrary height, and in the problem you actually go below that height, then it's possible your height could be a negative value at some point, which is fine. Your problem will still work out as long as you're consistent with your definition of your height. Anything above a certain point would be positive, anything below height as being your zero height. If no work is done on the system, then your initial energy will equal your final energy. If work is done on the system, the initial energy plus the work will equal the final energy, the one equation to rule them all. So in this equation, we need to evaluate the work. We know from Chapter 7 that is force times distance, cosine of the angle between their two directions. It could be positive or negative depending on that angle. For many applications, the force is going to be in the same direction as your displacement. So you're going to be adding energy to the system by pulling it along. Cosine of 0 degrees would be 1. It simply would be force times distance. If we're dealing with, a lot of times with friction, it might be working against the system at 180 degrees to the displacement. So that would be cosine of 180, negative 1. A lot of times with friction, it's simply going to be negative force times distance. So maybe 90% of the problems will be pulling force times distance or against the motion, negative force times distance. And then the other 10% might actually have an angle involved. But work is work. It's force times distance, cosine of the angle between the two vectors. Once you set this up, evaluate the work, evaluate your energies, set up your equation, eliminate the terms that are 0. And there are going to be a lot of terms that might be 0. So that's why you want to start with the one equation to rule them all. Immediately start eliminating the terms that might be 0. And then solve for the unknown. Let's try this out with a problem. A sled of mass m is given a kick on a frozen pond. The kick imparts to it an initial speed of 2 meters per second. Coefficient of kinetic friction between the sled and the ice is 0.1. Utilizing energy considerations, find the distance the sled moves before it stops. So we're going to kick this sled. The name of the sled is Rosebud. If you don't know what that means, you should watch one of the greatest movies of all time, quote unquote, Citizen Kane. Maybe I'll tell you about that later. All right, so we're going to go from point A to point B. We're going to write down our one equation to rule them all. Point B is a distance d away. Okay. Before we go further, maybe some of these terms actually might be 0, or I think I might have written down all the terms before. Okay, I did. All right. We're going to select our height as being the height of this plane. So the potential energy at A is going to be 0, because that will be our 0 height. And for that matter, potential energy at B is going to be 0, gravitational potential energy. And there's no spring involved, so the total potential energy at B will also be 0 as well. So 2 terms are already gone. We realize that even though we start off with a velocity of 2 meters per second, we're going to eventually come to rest at point B. So our velocity at B is going to be 0, and hence the kinetic energy at B will be 0. So already this equation's gotten easier. The kinetic energy at A plus any work done on the system is going to equal 0. Kinetic energy at A is 1/2 mass times the velocity at A squared. The work done on the system is work of friction, and it's working against the displacement. So that's going to be a negative force times distance for friction. If the friction is equal to mu times the normal force, and normal force is mg in this case, our frictional force is mu mg. So solving for d from this previous equation, we have d is equal to 1/2 mass times velocity at A squared divided by friction. But friction is mu mg. The masses cancel out. And our distance d is going to equal 0.5 times 2 meters per second squared over mu 0.1 times 9.8, 2.04 meters. So this sled will slide and stop after 2.04 meters. Great. Not an easy problem, but easily done using energy considerations. How about that? All right, I got to tell you about Rosebud. All right, if you don't want to hear about Citizen Kane and ruin the greatest movie of all time, quote unquote, then stop the video here. The lecture is done. But if you want to hear about Citizen Kane, just briefly, then I'll tell you about it right now. In Citizen Kane, it starts off, and you see this dying man. He's a very rich man, and you actually don't see him. You just see his hand, and he's holding a wine glass full of red wine, and you hear him say his dying words, "Rosebud, Rosebud, Rosebud." And so he dies, and the last words out of his mouth are Rosebud. So the whole movie's about who is Rosebud. You know, who possibly could be Rosebud that this rich dying man, the last thoughts in his life are about Rosebud. Is it some dancer he knew in Las Vegas? Who knows? So that's what they're trying to find out. All the media is trying to find out. And at the end of the movie, we find out that Rosebud was the name of the sled he had when he was 6 years old. He loved that sled. Name of it was Rosebud, and that's what he's thinking about when he's dying at the end of his life. Okay, ruined the greatest movie of all time for you. Go see it anyway, though. All right, we'll look at more examples in the next lecture video dealing